Okay, I'll take care of it. You start.
Okay, everybody. Today we're very lucky to have Professor Christine Aidala from University of Michigan. Christine did a PhD, I think that's at Brookhaven Lab, and then started on Phoenix, I believe.
For my PhD already, I was on Phoenix.
Yeah, Phoenix. She's been on Phoenix the whole time. Then she was at postdoc at Amherst, and then she was at Los Alamos, first as a postdoc, then as a fellow. And we interacted on the users executive committee at Brookhaven. Christine's a QCD person, but the kind of different kind of QCD that I do. But she's been very good today about reminding me that there's only one kind of QCD, and the little quarks don't know who's studying them, but they're just quarks and doing stuff. So today we'll have a lovely discussion about spin and momentum correlations and quantum interference, and sort of the second stage of QCD. Welcome, Christina.
Thank you very much. So yeah, the title I ended up with is Spin Momentum Correlations, Aharonov-Bohm, and Color Entanglement in Quantum Chromodynamics. Just to be clear, I'm an experimentalist. Some people have asked me about the title, which I guess gives a theory impression. So we've had our fundamental field theory of the strong interactions, quantum chromodynamics, in hand since the 1970s, so more than 40 years now. However, since the quark and gluon degrees of freedom in the theory, the degrees of freedom we have in our fundamental quantum field theory are not the ones that we can manipulate and work with directly in the laboratory due to color confinement. So quarks and gluons are confined to color neutral bound states. People saw that we needed, back at the founding of QCD, they needed an extra quantum number. They saw that they needed 3 charges to make a neutral, thought of the analog, the analogy to red, green and blue light, making neutral white light, and called it chromodynamics. So you can either have bound states of 3 particles, 3 quarks, each carrying a different color, or you can have bound states of a color, anti-color, 2 quark bound states, one carrying a color, the other carrying an anti-color. So because of color confinement, we can't observe these quark and gluon degrees of freedom directly in the laboratory. So that's made it take be quite a long haul as we've made progress over the years in QCD. So if you probe the proton at different energy scales, this offers information on different aspects of its internal structure. So just as you go to different wavelengths in electromagnetic wavelengths, looking at resolving smaller and smaller features of matter, so you're limited into looking at things the sizes of cells with your optical microscopes, and you can go to X-ray scattering to look at atomic structure, atomic lattices, also neutron scattering. If we want to look inside the proton has a radius of about 10 to the minus 15 meters, then we need high energies that we can only achieve at the accelerator facilities. And then depending on what energy you have, you can probe the whole proton more or less coherently. If you're doing, for example, elastic scattering, you can be at an energy scale or distance scale such that you're mainly sensitive to this valence quark structure. You can think of the valence quarks, these 3 quarks making a proton, as determining the quantum numbers of the proton. Or if you're at these higher energy scales, resolving shorter distance scales, you can look into also these quark-anti-quark pairs coming, fluctuating in and out of existence in the quantum mechanical sea of the proton. So I'll be talking a lot about quark and gluon distribution functions, so I'd like to introduce them. This is the language, one of the primary ways we've developed of talking about the internal structure of the proton so far. And whenever I talk about introducing this, I like to use these figures from a textbook by Halsen and Martin. So the basic question you're asking is, what momentum fraction would the scattering particle carry if the proton were made of different things here? So if I think of probing the proton with, say, an electron beam, think of the proton just as a black box. I'm going to shoot an electron in. If it's going to scatter, say, inelastically off the proton, I'm going to break up the proton to resolve something inside the proton. But if I am scattering elastically off of a subcomponent, then just by knowing the initial 4 vectors that I set up in the laboratory and measuring the scattered energy and angle of the electron, then I can reconstruct the 2-to-2 kinematics and have all the 4 vectors in my diagram. And so if I shoot an electron in, and the proton are really a point particle, so I shoot my electron in, my proton black box, I reconstruct the kinematics by measuring the energy and angle of the scattered electron. I see that whatever I struck inside the proton was carrying at that instant 100% of the proton's total momentum. So I get the spike. Every time I shoot it, I get 100%. So I get a spike probability distribution at the spike at 1. And this x is a scaling variable named after Iris Bjorkane, is why it's called that. If instead the proton were made of 3 non-interacting quarks, each carrying exactly 1/3 of the proton's momentum, every time I scatter my electron into my proton black box, I would reconstruct the kinematics and say, okay, whatever I scattered off of was carrying exactly 1/3 of the proton's momentum. And so I'd get a spike at 1/3. Now if I allow those, if I have instead in my proton 3 valence quarks, but carrying on average 1/3 of the proton's momentum, but now able to exchange a gluon among them, able to share some of their momentum among one another. So I'm going to smear out this distribution around 1/3. And now if I allow for a gluon to fluctuate into a quark anti-quark pair, and I take my snapshot, if I have a high enough energy electron to resolve this sort of fast time process, or small spatial distance process, that I take the snapshot and I've scattered off of the quark or the anti-quark, I'm going to increase the probability that I'm scattering off of something carrying a small momentum fraction of the total momentum of the proton. And if you're worried about having a fixed target and a beam hitting a stationary target, and you say, well, the proton has no momentum, so how can I talk about what fraction of the proton's momentum a particular quark is carrying? Well, if you're probing the proton inelastically, then in the center of mass frame, you're always in a boosted frame. So in the center of mass frame, your proton always has some non-zero momentum. So you can look at things in this picture. So this is sort of the framework that we've developed for talking about the behavior of quarks and gluons, the force carrier particles of the strong force, inside the proton. And this is a pretty close idea of what the actual picture looks like in terms of just this one-dimensional variable, where you're neglecting any motion, any orbital motion or transverse motion. You're just considering that the quarks inside the proton are moving exactly parallel, exactly collinearly with the parent proton. So I'll also be talking a lot within the framework of perturbative QCD. So the idea is that you're taking advantage of the running of the strong coupling constant with energy. This is known as asymptotic freedom, that you have weak coupling at high energies or equivalently at short distances. So if you think of the electromagnetic coupling constant, alpha EM, so approximately 1/137, and the fine structure constant. This also changes with energy, but much more slowly than the strong coupling constant does. So if I'm at an energy scale of less than 1, so this is the fore momentum transfer in a scattering reaction. So this is the strong coupling constant. It changes rather rapidly as a function of the fore momentum transferred in a scattering interaction. And so if you're at about 1 giga-electron volt energy scale, then you have strong coupling greater than 0.5, going up toward 1 here as I go below 1 GeV. If instead I'm at high energies, 10 GeV, I'm at about 0.2. If I go up to 100 GeV, I'm closer to 0.1, and I can do Taylor-like expansion, right, in increasing orders of this strong coupling constant because I'm taking higher powers of something that's significantly smaller than 1 and create a series that hopefully converges. So
what's the significance of the open versus filled symbols there?
Oh, for the heavy, what were these from?
You got different shapes, but you also got
the filled and unfilled. I'm afraid I don't remember.
This is not your figure.
This is not my figure.
Okay.
I should put I have the date. It should be a Hera figure, but I should have the date, the reference for it, and then we could look that up. So you can do a perturbative expansion, as is commonly done in quantum electrodynamics calculations. However, one thing to keep in mind, even when you are in this high energy regime of QCD, so you can do these perturbative expansions. Think again of sort of a Taylor series kind of expansion. You have many more diagrams than you do in the case of quantum electrodynamics because of the fact that gluon carries color charge itself. So gluon does couple to itself, so you can have 3 gluon and 4 gluon vertices, unlike the case of the photon in quantum electrodynamics, so the photon does not carry electric charge, so you don't have the photon coupling to itself. So you quickly things get more complex much more quickly in QCD compared to quantum electrodynamics. So very importantly, these perturbative techniques, when you are in a high energy regime, provide one rigorous way of relating our fundamental field theory to a variety of physical observables, because that's going to be the whole ball game here. We've had our fundamental theory since the 1970s. The trick is being able to relate calculations done with that field theory to things that I can measure in the laboratory. So how far have we come? So QCD is challenging because of the fact that the quarks and gluons are confined to color neutral composite states. And I look at the 3-decade period after the initial birth of QCD as having been dedicated to discovery and development. I think you can argue that this could have been a few years earlier, but I think at least the symbolic closure was the awarding of the 2004 Nobel Prize to Gross, Politzer, and Wiltshire for the asymptotic freedom in QCD. And I look at us as having recently entered a second phase that I look at as quantitative basic research in QCD. So I think a lot of fields go through this very long arc of having an initial period of discovery and development, a second period of quantitative basic research, and in some cases you move on eventually to a third period of application. So personally, my gut feeling is that in the next 50 to 100 years, we will have some applications. It's the proton, it's the nucleus. So for understanding the partonic structure, the quark and gluon structure of protons, I don't know what those would be. If it's more efficient fusion energy reactions or something like that. That's beyond my career. I'm really excited that that I'm going to be working my way through these years of basic quantitative research in QCD. So why do I think that we're in this, the early years of basic quantitative research in QCD? So in perturbative QCD, since the 1990s, in particular, we've been starting to consider more detailed internal dynamics. So rather than this static picture that I gave you of just looking at this one-dimensional snapshot, looking at the co-moving momentum fraction of quarks and gluons inside the proton, we're starting to look at some more dynamical quantities. And crucially, to be able to perform phenomenological calculations using these new ideas and tools. So we don't just have theoretical ideas, we can work them all the way through to a calculation that can be compared, hopefully as apples to apples as possible, with experimental measurements. So let me give you some examples here. I'm going to illustrate each one of them. So I'm talking about various resummation techniques, nonlinear evolution with the the energy scale at smaller momentum fractions, so looking at the C quarks and gluons. Spin-spin and spin-momentum correlations. So spin-momentum correlations are very clearly a dynamical quantity that you can look at now, that people do look at now, that they didn't look at 20 years ago, or 25 years ago. And spatial distributions of quarks and gluons in QCD advanced states. So the word parton is just a general term for either quarks or gluons. And then in non-perturbative methods, so lattice QCD, where you discretize space-time and do calculations on this lattice, is less and less limited by computing resources since just 2010. The lattice QCD community has been starting to perform calculations at the physical pion mass, so this is basically an input for them. And so it was 36 years of lattice QCD calculations before they got to this point, and they've only gotten to that point for a handful of specific observables or calculated quantities. Plus there's some recent new ideas in lattice QCD on how to calculate previously intractable quantities, which I'll talk about. And then this certainly isn't quantitative at all, but something known as the gauge-string duality. So relating some string theory techniques, this duality with conformal field theories. QCD is not a conformal theory. There's so it does have a particular scale, which is the hadronic binding scale, so lambda QCD, a few hundred MeV. So it's not clear where this can go, if anywhere. The reason I think it's somewhat exciting is because it's the first fundamentally new handle to try to tackle any kind of strongly interacting system such as QCD, in decades. So we've had perturbative calculations since the 1970s. We've had lattice QCD since the 1970s. We've had all sorts of low energy modeling since before QCD, actually, in the 1950s, whatever. And so this is something new, and I'm curious to see what people can do with it over the upcoming years, if anything. We'll see. So I'd also like to say a few words about effective field theories. So QCD exhibits different behavior at different energy scales, density scales. So effective field theories can be useful approximations within different regimes. So just a couple examples that have come out over the last 15 years. Color glass condensate. This is relevant when you're in a high energy and high density regime. Something known as soft collinear effective theory. It's not really related to a specific energy regime of QCD, but it's provided new insights into performing complicated perturbative calculations much more quickly than previously possible. Oops, I pushed the wrong button there. Some a little bit less recent effective field theories are heavy quark effective theory, non-relativistic QCD, and we have many effective theories that have been around, a lot of them for a long time, and non-perturbative QCD, such as involving chiral symmetry breaking, things like this. So let me walk you through some illustrations of some of these developments that I've highlighted that have taken place in the last 15 to 20 years that are the reasons, some of the reasons that I think that we are in now a quantitative era of basic research in QCD. So this is something known as threshold resummation. Don't worry about exactly what that is. So, this has allowed us to extend perturbative calculations down to lower energies than are previously possible. The basic idea of all of these resummation techniques is if you have observables with two different scales. So in this particular case, we have the center of mass energy, which is 23.7 GeV in this case. This is old experimental data from CERN. And then it was measuring proton-proton collisions going to two neutral pions plus something else that you didn't observe. And they looked at the invariant mass of the pion pair. So we've got two scales here. We've got the center of mass energy and the mass of the pion pair. For observables with two different scales, we can sum logarithms of their ratio to all orders in the strong coupling constant. And so if we're doing a perturbative calculation in expansions of powers of the strong coupling constant, think again of your Taylor expansion, if you will, in terms of alpha strong, you're going to truncate that at some point, usually after just, say, the second power of alpha strong, actually, because you get so many diagrams quickly, especially when dealing with hadronic final states as opposed to simpler final states. You're recovering by adding in these resummed terms. You're recovering some of the terms that you've truncated in your Taylor expansion, if you will. So you're getting back part of what you've lost in your truncated calculation, and you've improved your calculation. So here you can see, so this was this old data in the early 90s. The center of mass energy. So these were the earlier calculations, the blue dashed lines here. You can think of this as a band, sort of an uncertainty band on the theory calculations. So people got the slope very nicely, described the data, but it's off by, well, let's see here, we're off by about almost an order of magnitude, right? Maybe a factor of 5 or so, I guess. So this is 2 times 10 to the 2, and the point is up here at 10 to the 3. So now these red lines, red solid lines, include these resummed terms, this particular technique, and they get not only the slope, but now they've also reduced the uncertainty band, right? So the width between these two red lines is reduced compared to the width between the blue lines, and we've got quantitative description to within sort of 20% rather than the factor of 5. So we've gone from a qualitative description, getting the slope right but not the magnitude, to a quantitative description. Here's another example illustrating a nonlinear regime of QCD. So the basic framework for nonlinear QCD, in which gluon densities are so high that there's a non-negligible probability for two gluons to overlap and combine to a higher momentum, a single higher momentum gluon. This was developed in 1997 to 2001. But okay, if this was developed in 97 to 2001, how could these authors get away in a peer-reviewed journal? This isn't like a conference proceedings or something, right? This is PRD, 2009, right? So 8 years after this development took place. And look at their title, Nonlinear QCD Meets Data, a global analysis of lepton-proton scattering with running coupling BK evolution. Don't worry about what running coupling BK evolution is. the reason that they could get away with a title like Nonlinear QCD Meets Data 8 years after all these ideas had been basically developed was because you needed this additional phenomenological ingredient into the theory to be able to perform calculations that could be directly compared to experimental data, right? So again, the whole business in QCD, it's not that we need to find the underlying theory. We've had the underlying theory since the 1970s. We need to understand how we can best apply, or most extensively, apply that theory to quantities that I can measure in the laboratory. And so here we have these fixed proton structure function data at very low parton momentum fractions x. So where you're deep into the C, where you have your gluons splitting into quark-antiquark pairs, and loops going back into gluons, and if your gluon densities are so high, they can recombine, and this is where you get this nonlinear regime. And they seem to have, these are fits to the data, so rather than a priori calculations, but still, this missing ingredient allowed us to go from basic ideas that were developed in the last 20 years to just 2009, so that we could really make quantitative calculations and compare them to experimental data. So another example, spin-spin and spin-momentum correlations in QCD bound states. So the picture that I showed you from the textbook just talked about the probability of scattering off of a quark of any flavor, carrying a certain momentum fraction, moving parallel, so collinearly, with the motion of the proton in the center of mass frame. So that would be these distributions here. So that was a lot of the focus for the first decade. The very first inelastic proton-electron scattering experiments took place in the 1960s at SLAC. In the 1980s, saw the first polarized proton inelastic scattering measurements, and you can look at spin-spin correlations. So now here are all of these pictures. The external circle is the proton, the internal circle is a quark. The arrows attached to them are the spin directions, and the beam is moving, you can think of it horizontally. So then this would be a spin of the proton parallel, longitudinal, so parallel to the beam direction. And then this would be the spin of the quark, also longitudinal, again with the reference frame, the boost frame, center of the beam direction. So this is now the difference in probability of scattering off a longitudinally polarized quark inside a longitudinally polarized proton. That's where the quark is parallel versus anti-parallel to the spin of the proton. You can do the same thing with the transverse case, and John actually founded this field back in the late 1970s. The reason that these two aren't related by rotation is because rotations and boosts don't commute in quantum mechanics. Then you can also look at spin momentum correlations. This again ties directly to looking at dynamical quantities. So if I don't neglect or integrate over any transverse motion, but instead I allow for jiggling around of the quarks inside the proton, or orbital motion of the quarks inside the proton, if I allow that explicitly, then I can get these different kinds of spin momentum correlations. They all have the form of triple products of one spin and two non-parallel momenta. If these are parallel, then this would vanish as the vector product of parallel vectors. So I can talk about this one in particular. So here we have, it's looking at a correlation between the spin of transversely polarized proton, and you can think of the orbital motion of a quark inside it. And you can get different mix and match, whether you're talking about the spin of the quark or the spin of the proton, what two momenta you're looking at. And what isn't interesting is, it's not interesting that you can just mix and match, write down these mix and match combinations on a piece of paper mathematically. What's going to be interesting is that a lot of these have been measured to be non-zero in nature, which I'll talk about more in a few minutes. So my last example for working within the framework of perturbative QCD is exploring spatial distributions. So there's some initial evidence from electron-proton scattering experiments where they're looking at a process called deeply virtual Compton scattering. They found some initial evidence that quarks carrying larger momentum fractions in the nuclei are distributed over a smaller volume in space. These are what I would call sort of pioneering measurements here, and these are very schematic diagrams here, already processed with respect to the experimental data. But this is something that we couldn't do at all 20 years ago. Similarly, there's some work going on here with Michael and Daniel looking at J-psi and upsilon production in ultra-peripheral nuclear collisions, which is sensitive to the spatial distributions of gluons in the nucleus, or you could do the same thing with protons if you wanted to. So looking at lattice QCD, this was a talk shown by Suda figure in the lattice, senior Japanese lattice QCD guy at Panic 2011, which showed the very first calculations of this is the actual mass of the pion. So you can see there are a lot of calculations being done. And it's for technical reasons. They don't have the computing power to be able to do things. So historically what's been done is you do things where you can handle the numerical calculations and then you do an extrapolation down to where you think the real physics should actually be. So now they're starting to do, since 2010, 2011, these first calculations at the physical pion mass. And then this is a paper from 2013, although there's some controversy surrounding it. So it was an idea proposed by Shangdong Ji, who's coming from the perturbative community, not really the lattice community, so he came in as a little bit of an outsider. He suggested that rather than just calculating moments, so integrations over momentum fraction is what you can do, so which is fine in theory, but the experiments you never get to the zero momentum or the 100% momentum fraction, right? And so you're always truncating some region experimentally, even though the lattice theorists could calculate was the full integral from 0% momentum fraction to 100% momentum fraction. So it's been hard to get apples to apples. He has this proposal such that you could actually calculate the functional dependence on the momentum fraction. So there are a few papers starting to come out about that, but there's some debate about whether this is really going to work. So
is that supposed to be the neutral pion mass or charged pion mass? Because it needs to be neutral pion without charge.
Well, yeah, okay, so then it would be the neutral pion as opposed to the 139 for the charged pions. I assume they can do it using any pion they want as long as they control what they're doing. So you have the isospin symmetry of the neutral pion. And I don't know enough about how lattice do their calculations and extrapolations, but I guess it would be, if anything, slightly easier to do slightly larger number for 139. So then effective field theories. So here's an example taken from soft collinear effective theory. This is before the Higgs announcement in 2012, but it's looking at gluon-gluon fusion to the Higgs boson, the transverse momentum distribution, and for this very low transverse momentum portion where it's turning over here with these next NLL, what are labeled as LL and NLL calculations for next to leading log using these free summation techniques. The Higgs transverse momentum is actually due to the intrinsic transverse momentum of the two gluons that are fusing, so it's like the vector sum of the transverse momenta of the two gluons that lead to the total transverse momentum of the Higgs for low transverse momenta. And you can do these kinds of calculations within the framework of soft collinear effective theory or within the framework of transverse momentum dependent parton distribution functions. So these two different alternative ways that are possible to do these kind of calculations. So if I want to map out in 2015 the quark and gluon structure of the proton, there are a lot of questions I can ask now, not many of which I wasn't really in a position to ask a few decades ago, or the community wasn't in a position to ask. So if I open up undergraduate textbooks, I could think of quantities like position, momentum, and spin. And in this business we have flavor, so the flavor of quark like up, down, charm, strange, or color. Of course, we're in QCD, Chromodynamics. So in order of what we know from most to least, so the vast majority of the past 4 decades of inelastic scattering experiments studying the internal structure of the proton have focused on this one-dimensional momentum fraction, one-dimensional momentum structure, where you're neglecting any jiggling around or orbital motion. You're just looking at the collinear momentum fraction. However, since the 1990s, we've been starting to consider the transverse components, orbital motion, spin. Polarized protons were first studied in the 1980s, so early 1980s, as opposed to late 1960s for these inelastic unpolarized experiments. However, how the angular momentum of the quarks and gluons add up is still not well understood, actually. In terms of flavor, so up-type quarks and down-type quarks, we have good measurements of flavor distributions in this higher momentum fraction region, but we have had some surprises in the last 10 years for lower momentum fractions. That's the focus of my experiment at Fermilab, actually. And then position, you might think position and momentum, well, phase space, right? These should be the first things we could ask about. Remember, the proton is very small, but it's got a radius of about 0.8 times 10 to the minus 15 meters. So you can ask, okay, well, what's the probability of finding an up quark 2/3 of the way from the center, and, or right at the center, or a gluon? We had no clue how to measure this, or how to think about it, until the mid-1990s. And so the theoretical concepts with some experimental proposals were only born in the mid-1990s, and there have been what I would call pioneering measurements over the past decade, a couple of which I showed. And then, of course, color was accounted for theoretically from the beginning of QCD. People saw they needed another quantum number. 3 charges make a neutral, let's call it color. But some more detailed, potentially observable effects of color have come to the forefront in the last few years, which I'm pretty excited about. So I think a lot of fields tend to go through a cyclical process where you have periods of proliferation of observations, ideas, and then you go through a phase of synthesis. So QCD and hadronic physics has certainly already been through this once. So if you look at the 1950s and 60s leading up to the birth of QCD, right, we had this explosion of new particles being observed in different kinds of scattering, nuclear scattering experiments. And then we had our sort of periodic table with the quarks, so people coming up with the quarks, Neyman and Gelman. And then the birth of QCD, so it was certainly a period of synthesis. I think the 1990s really was another period where we had a lot of new ideas coming out. The 1990s and right around the very early 2000s. And I think now we've been going largely through a period of synthesis, which I've been really excited to see. So even working at the Relativistic Heavy Ion Collider for the past 14 years now, and I've been focused on the proton structure program there. We have polarized beams there, up to half TeV, center of mass energy, and it's variable. The lowest collision energy we've run with polarized protons has been 62 GeV, center of mass energy, so from 62 to 510 GeV. And then we've run heavy ions all the way up through uranium. The two communities that came together at the Relativistic Heavy Ion Collider when the facility was being designed and built in the 1990s, they were really just brought together by the fact that the facility had capabilities, so you could design capabilities relevant to both communities, not because they identified any common physics goals. But I think now a lot of what we do, so looking at the partonic structure of the proton, now the heavy ion community is much more interested in the initial state, what's the partonic structure of the nuclei before they actually collide. So I know my initial conditions leading up to formation of a quark-gluon plasma when I collide two heavy nuclei. So I think the two communities have really been coming together a lot over the last 15 years. So a few words about factorization and universality within the perturbative QCD framework. So in QCD, you need to systematically, well, if you want to work with perturbative functions, you need to systematically factorize, so separate short and long distance physics. Any observable physical QCD process is always going to involve at least one long distance scale. So a hadron, right? In the lab, I'm never working with a quark or a gluon. I'm always working with a bound state that has got a radius of 10 to the minus 15 meters or something. And so this is a long distance scale. And that's not something that I can calculate a priori using this perturbative expansion. So these long distance functions, like describing proton structures, so these are not directly calculable within a perturbative expansion from the primordial theory. They need to be universal in order to be portable across calculations for many processes. So I work mainly with proton-proton collisions at the Relativistic Heavy Ion Collider, also at Fermilab. But I certainly take advantage of a lot of prior knowledge that was gained from electron scattering off of protons over the past 40 years, and I can use what we've come to understand about the structure, the quark and gluon structure of the proton from electron scattering, and now I can use those descriptions of the proton as input to calculations for proton scattering. So that's the idea of universality, to be portable across calculations for many processes. And so we measure can constrain from lots of measurements around the world, different processes, these partons, so quark and gluon, distribution functions, as well as fragmentation functions. So even after I've scattered a quark out of a proton, I'm not observing that scattered quark. It's going to turn into a spray of particles in my detector. I'm going to measure some or all of them. Bound states, QCD bound states. Then I'm going to measure these non-perturbative functions in many different colliding systems over a wide kinematic range, and what we do is constrain them, so improve our understanding of proton structure or of the process of a scattered quark turning into final state particles by performing simultaneous fits to world datum. So now I focus in on spin momentum correlations. So there was a discovery in 1976 in polarized proton collisions, very early polarized beams. It was a pretty simple, conceptually, experiment. So they had a transversely polarized proton vertically up. They're measuring pion production, so the lightest QCD bound state. They're pretty easy to produce. They're so light, you don't need very high energy collisions to produce them in abundance. And they saw that up to 40% more positive electrically, so this is electric charge, plus and minus, positively charged pions went to beam left than beam right with the spin of the proton beam up, and up to about 20% more of the negative pions went to beam right than beam left. So they saw this very big angular asymmetry in the different charges of the pions when you had a vertically polarized proton beam. So this is, people are looking for, effects of 10 to the minus 6 or 10 to the minus 20 or whatever. This is 40%, right? It kind of hits you in the face, this big an effect. But we actually the community had to wait more than a decade, really, for the birth of a new subfield in order to explore the possibilities of what could be generating this. And this variable here is called Feynman X. The F stands for Feynman. And here would be, so closer to 1 is closer to the beam direction, basically. So this was greater asymmetries, closer to the beam direction, more forward. So 1990, so that was 1976, that discovery. So it wasn't until 1990 when a theorist named Dennis Sivers, who was working at Argonne National Lab at the time, proposed a mechanism in an attempt to understand the observed asymmetries. It departed from this traditional collinear picture where you neglect any jiggling around or orbital motion, and proposed a correlation between the intrinsic transverse motion of the quarks and gluons and the proton spin. So if you want to naively think of it, if I've got a spin up proton, well, I could have maybe the up quarks are orbiting around like this, and maybe the down quarks are orbiting the other way, and this could be possibly leading or contributing to the two different signs of the pion asymmetries that we see. So this was the first transverse momentum-dependent parton distribution function describing a spin momentum correlation inside the proton. And this really opened up effectively a new frontier where people started to become much more focused on quark and gluon dynamics inside QCD bound states, as well as in the process of hadronization. So I showed this before. So now I've added the names to some of them. Some of them are related to sort of distributions themselves, helicity, transversity. Others are named after theorists. These worm gear ones are related to the fact that you have something transverse and something longitudinal. So there's a particular kind of gear where you can put in transverse motion in one direction and create motion for a particular direction. This pretzelosity, it's sort of a quadruple looking thing. People thought it looked like a pretzel, they called it pretzelosity. So as I said, what's important isn't that we can write down all these spin momentum correlations mathematically. What's important is that we have a lot of evidence from deep inelastic electron and muon proton scattering experiments over the past about 10 years now that many of these are non-zero in nature. So I'm going to flash a lot of data. Don't worry about what the details are. I want you to focus on the magnitude of the effects. Just the fact that we're going to be looking at a bunch of different terms, so different spin momentum correlations. And we're looking at several different collision systems too. So this one has been measured in electron-proton and muon-proton systems, sort of 5–10% level effect. So not 40, but still quite sizable, 5–10%. This is another pair. This is measured in electron-proton collisions in this plot. Again, sort of 5–10% level effect. This is yet another pair, and again, sort of 5-ish, 10%. This is electron-positron annihilation. You say, okay, where are the protons? So this is a spin momentum correlation in the process of hadronization. So again, right, this is a really neat measurement. So you have electron-positron annihilation. It's a quark-antiquark pair. And you don't know, and then they go off and form two jets of particles, sprays of particles in opposite hemispheres. You don't know which one was the quark and which was the antiquark. You don't know the spins of the two, but you know that they annihilated via a virtual photon. The virtual photon has spin 1 h bar, and so whatever the spin 1/2 quarks are, their spins have to be correlated. So they're the same direction as each other, because they came via this virtual photon decaying to a quark-antiquark pair. And so you can look at the angular distribution of particle production in one hemisphere with respect to the angular distribution in the other hemisphere, and gain information on the spin of the quark that led to that particle production. So it's a pretty neat measurement looking at E plus E minus, and Babar got into the game as well and confirmed the measurement from Bell in Japan. So both the factories have now confirmed that, and again, it's sort of, here's 10%, right? So it's right there, sort of 5–10% level spin momentum correlation. So now those were all E plus E minus and electron or muon scattering. What about these proton-proton asymmetries that went not to 5–10%, but up to 40%? So they have, this is the 1976 discovery measurement that I showed you a few slides ago. This has been confirmed at a series of higher and higher energies over the years. And I was really glad I had the opportunity to make this plot for a CERN Courier article in 2009, because I had been showing these different experiments, but taken from the original papers, so I'd never put everything on the same axis ranges to see just how strikingly similar this is over this. It's more than an order of magnitude increase in energy. So this is the Brahms experiment, which KU was involved in. And I guess you guys weren't directly involved in this measurement, but involved in the broader experiment. So this is at the relativistic heavy ion collider. So we have these strikingly similar effects across energies. So it suggests that we have this continuum between regions where people wouldn't try using this quark distribution function language and perturbative techniques to try to describe the data, to regions where they would. Right? So I think that's really important, that it's giving us a handle where we can do calculations and try to understand things, relating them down, a handle down to regions where we can't do calculations right now. And you might, okay, those of you who are familiar with these perturbative calculations, you might say, well, I didn't show you what the hard scale was. So transverse momentum of a produced particle is usually the typical proxy used to set the hard scale. Any motion that's perpendicular to the beam axis, was generated in the scattering, right? So it's far away from the initial momentum vectors that you put in to your initial state. So this is now a center of mass energy of 500 GeV, so half a tera electron volt. This is only at somewhat forward, so it's only at about 0.2, this variable here, so it's actually right around here, right around where it's turning on. But now this was 62 GeV, so this is even higher energy, and this is now versus transverse momentum. So this is the hard scale, so this would be at about 7 GeV, so the alpha strong is about 0.2. So we're comfortably in a region where people very typically apply perturbative calculations, and we still get, we don't have the detector configuration, unfortunately, to measure it more forward, where we might see something 20 or 30 or 40%, but this 2% here, it's very clearly non-zero in the forward region, consistent with zero backward. We still see these effects at these very large scales where we can apply perturbative PCD techniques. So there are always these huge effects when we do proton-proton to pions, ahedrons. We've measured other particles too, which have been pretty interesting. So antiprotons also show a large asymmetry, which Brahms measured as well, which is pretty neat. People don't understand that still. However, if you're doing proton-proton to pion production, you don't have enough information to separate what's going on inside the proton structure, so what was a spin-momentum correlation in the proton structure, versus, is it effect, well, after I scattered a quark out of my proton, was it a spin-momentum correlation in the process of hadronization to a particle that I observed in my detector? So this complication in PP collisions has led people to, do some more thinking about what could be going on, and some really neat stuff has come out. Going a bit through a historical tour here, one of these particular spin-momentum correlations, or two of them actually, are naive under what's called, are odd under what's known as naive time reversal. It's actually a parity time reversal transformation. I still don't understand historically why people call that naive time reversal, but that's the language used in the literature. And so I told you that this theorist, Dennis Sivers, had explained the early 40% asymmetries from 1976, original discovery, in this 1990 paper. proposing this new spin momentum correlation. Well, it was shot down a few years later, saying that such functions had to vanish because of this naive type T-odd behavior was forbidden in QCD. And it was only realized in 2002 by another set of three theorists, Brodsky, Bohm, and Schmidt, that this could be non-functional, this spin momentum correlation, a particular one, could be non-vanishing if you had phase interference effects due to color interactions.
Now I have to stop.
Uh-oh, okay. Yeah.
There's been many PT-odd things before Sivers and
Yeah.
board holders and everywhere. And the lesson of all of that has always been that time reversal is unreliable. The
Yeah.
reason is that no experiment is a time reverse of another experiment.
Sure.
I'm sure you know.
Yeah.
So amplitudes that are time reversal odd or PT-odd
Yeah.
are often listed and dismissed and then said, well, we don't expect to see that. And every time they're seen in nuclear physics. And in nuclear physics is when we had some final state interactions,
Okay.
but not in the initial analysis.
Yeah. So
So-
you say this is history repeating
So I
itself.
think Collins had a more subtle angle for dismissing Sivers.
Okay.
But certainly Brodsky, Bohm, and Schmidt made it look as if Collins didn't know physics, and they did.
Well,
So
Collins
they
admits.
capitalized on this particular
Yeah.
channel of making it interesting.
Okay.
So
Okay.
it's a general phenomenon. That
Yeah,
this
yeah,
time
Dennis-
reversal
yeah.
never works.
Yeah. Dennis
And their
Sivers actually
explanation has
says he was
nothing
never
to do
convinced by
with their
Collins'
science.
argument. But the community listened to the argument at the time historically, so it was largely dismissed, is my understanding. Whether or not it should have been.
So I dismissed it when Sivers showed me. I said, that's a dumb idea.
Okay.
Everybody knows this exists, but
Yeah.
it's a dumb thing to work on.
Okay.
But it wasn't. It was a good thing to work on.
Okay.
So that.
I was wondering where you were going with that.
My objection is to give credit to Brodsky and so on for
Oh.
having noticed anything about this.
Okay, so
Everybody knows.
Dennis Sivers said that he knew all along that this wasn't an issue, but he left the field and took over his family real estate business in the meantime through his own historical timeline, and only came back into the field after, I was at the very first workshop in 2004, where he re-entered physics after more than a decade because this had gotten resurrected in 2002, and people had been talking to him and sort of asked him to get involved again.
You're a lot more wealthy by then.
So, I should finish up here. So, if you take into account the fact that you can have these quantum mechanical interference effects that allows this to be non-vanishing, then Collins, he did notice the error of his ways pretty quickly actually, and just a few months later he put out another paper in 2002 where he pointed out that if you have different processes, you can get a different sign. So if I have an electron scattering a quark out of a proton, then let's say that in the moment that I scattered, this quark was carrying the color red. Quarks are always exchanging their color via gluon exchange, so let's say in the moment that I scattered this electron off the quark and the proton, it was red, then the remnant of the proton the quark just scattered out of is by definition anti-red, so it was a color-neutral proton to begin with. So now if I have gluon exchange between a scattered quark and the remnant of the proton it was just scattered out of, this is going to be a red anti-red object interaction. And instead, if I have quark-anti-quark annihilation to, say, an electron-positron pair, so it's this diagram flipped on its side, so whether you have T-channel or S-channel processes, so now I have a quark coming from here, annihilating with an anti-quark coming from this proton. So again, let's say that in the moment of annihilation, this was a red quark annihilating with an anti-red anti-quark. So now if I have either gluon exchange between the scattered quark and the remnant of this one, or the scattering anti-quark and the remnant of this one, I'm going to have a same color interaction. So this is now red-red. This was red anti-red. What you get is an opposite sign for this this particular spin momentum correlation when measured in these two different processes. So we have this already measured, and we have these sort of 5–10% correlations that we've measured be non-zero. The race is on. Should try to measure this process. So the problem is getting high intensity polarized experiments to do that experiment. But now in terms of history repeating itself, I think it's really neat. So this is an excerpt from this 1993 paper that claimed that these naive time reversal odd processes had to vanish. What he wrote was, we have ignored here, in his argument saying that it was impossible, that it would vanish, we have ignored here the subtleties needed to make this a gauge-invariant definition. And so what we find out is that you couldn't neglect the subtleties needed to make this a gauge-invariant definition. You needed to use full-blown QCD to do this calculation correctly. And if you look back on people not realizing the importance of gauge invariance in quantum theories, this takes us back to Aharonov-Bohm in 1959, Physical Consequences of a Gauge-Invariant Quantum Theory. So just looking at Wikipedia, where I would not go for my Middle Eastern politics, but it's not so bad for physics and mathematics often. So I was really pleased that they have not just the, what's more familiar perhaps to a lot of people about the solenoid sort of example, but this language about physical effects of gauge-invariant quantum field theories. So the Aharonov-Bohm effect is important conceptually because it bears on three issues apparent in the recasting of Maxwell's classical electromagnetic theory as a gauge theory, which before the advent of quantum mechanics could be argued to be a mathematical reformulation with no physical consequences. The Aharonov-Bohm thought experiments and their experimental realization imply that the issues were not just philosophical. The three issues are whether potentials are physical or just a convenient tool for calculating force fields, whether action principles are fundamental, and the principle of locality. And then there was a Physics Today article in September 2009 on the Aharonov-Bohm effects, variations on a subtle theme, where the authors said, Aharonov stresses that the arguments that led to the prediction of the various electromagnetic Aharonov-Bohm effects apply equally well to any other gauge-invariant quantum theory. In the standard model of particle physics, the strong and weak nuclear interactions are also described by gauge-invariant theories, so one may expect that particle physics experimenters will be looking for new Aharonov-Bohm effects in new domains, and that's exactly what we are doing with this. So this is a manifestation of the Aharonov-Bohm effect in QCD, where we have these quantum mechanical phase interference effects. And so I've been trying to talk to some of my condensed matter colleagues about this to try to get more common language, because I don't speak this kind of language natively, if you will. And we actually had Philip Kim, who's a graphene guy who recently moved from Columbia to Harvard, gave a colloquium a few months ago at Michigan, and I was talking to him about this. And if you're familiar with the solenoid example that's in some graduate quantum textbooks, so you have a solenoid, it's one of the electromagnetic Aharonov-Bohm effects. You have a magnetic field inside a perfect solenoid, field-free region outside, but you have a vector potential. Then you pass an electron on one side versus the other side, and you get a phase difference whether you pass on this side versus the other side, dealing with quantum mechanics, so you have a phase in the wave function, right? And so he said, well, how are you adjusting the field of your solenoid? What's the analog? And so what we're doing, we're constrained to having always 180-degree phase shift. So it's always pi. We do it by using two different processes, and we always get 180-degree phase shift, whether we set up our color region and our color-free region with a vector potential outside of it this way or this way. And so
once more.
Yeah.
No.
No, you object.
No, the way Collins did the calculations is very naive.
Yeah.
He gets a minus sign because he doesn't really do any dynamical calculation.
Yeah.
These phases have been around a lot longer than that.
That's
And
fine.
the thing you know
Sort
you
of.
cannot calculate is strong interaction physics as a phase. So you should see something from the analytic continuation. But -1 is not a prediction of QCD. -1 is a prediction of the people debating this.
This one's a fiction. So you don't even need QCD for this prediction.
Absolutely. You don't even
This
need-
would come out of a positronium measurement if you could
No,
possibly
you don't
measure
even
the
need a
things
gauge
small enough to
theory.
do.
These are phases. These are just phase effects. And
Yeah,
right in
the phase effects come with the geometry of so you can think of also Berry phases.
Yeah,
The geometry of
the Berry phase, Bohm-Arahan, it's all very nice and stuff.
Okay.
And the connection you're making is not deceptive.
Yeah.
However, the actual underlying physics is that the entire field simply ignored all phases
Yeah,
for
okay.
a long time. Okay, then
Sure.
one naive and let's say simplistic, deliberately simplistic, disingenuous analytic continuation
Yeah.
gives you a minus sign. Everybody knows, I maintain,
Yeah.
that you should get a change of the phase But -1 is neither a property of the gauge theory, nor QCD, nor the actual thing when you measure it.
So you're arguing it's not a factor of -1, or you're just,
It's
it
minus
is a
one.
factor of -1,
The
but
change in
it's
phase
not
is
what I'm
just
saying
fine.
it is. Okay,
Now someone needs to make a decent calculation.
that's other than -1.
Yeah.
So people are doing that for the more complicated cases that I'll talk about in a second. So the simplicity of these two processes, so these are actually, the 2 to 2 scattering diagram is mediated by a virtual photon. These are QED processes, right? The only place a gluon comes in is in this interactions, initial or final state interactions. So the abelian versus the non-abelian nature of the gauge group, the fact that gluons couple to themselves in QCD, unlike photons, which do not couple to themselves, if you're in QED, doesn't play a major qualitative role. So in QCD, since you do have this non-abelian nature of the gauge group, gluons couple to themselves, you can get more new predictions that wouldn't come out of QED systems. Yeah, I gotta finish up here. That's my last few slides. So in 2010, Ted Rogers and Pete Mulders predicted color entanglement in processes involving PP to hadrons. So here you have lots of places where gluons could fly around, right? So before we had either an electron and a proton, or electrons in the final stage. Here we have QCD in the QCD bound states in the initial state and in the final state. Different paths for gluons to be exchanged. So, and this is for specifically if quark transverse momentum is taken into account in the calculation. You have to measure observables that are sensitive to it. The quarks then become correlated across the 2 protons, so entangled across the 2 protons. And this is a consequence of QCD specifically as a non-abelian gauge theory. So one of the questions that's out there is, are these huge 40% transverse single spin asymmetries in proton-proton collisions a color entanglement effect? So right now, the thing I'm most excited about in my own work is trying to test this to find the first ever evidence of color entanglement of quarks across protons, testing the Aharonov-Bohm effect in QCD as a non-abelian gauge theory. So we have no idea what the correlated states would look like. So the best we can do is try to make predictions, assuming no color entanglement, make a measurement that should be sensitive where you would expect, or it's predicted, color entanglement has been predicted, and look for a discrepancy. And so right now, though, the first thing we need to do is to get better predictions. So we don't have very good predictions. I'm working with unpolarized data because the prediction holds for polarized or unpolarized data when explicitly taking into account intrinsic transverse momentum of the partons, of the quarks and gluons. And so we have just a lot more data that's unpolarized over the decades than we do that's unpolarized. So here, example, looking at the, just like I said for the glue to Higgs, here we have quark-antiquark, the Z-boson production, and at the lowest transverse momenta of the Z-boson produced, the transverse momentum of the Z-boson is due to the intrinsic transverse momenta of the quark and antiquark. So we're doing these sort of simultaneous fits of a bunch, there's just 2 bins that I show here, a bunch of different world data over a wide range of energies. This is fixed target quark-antiquark annihilation data at 0.039 TeV center of mass energy. Here's at 2 GeV center of mass energy, and quark proton-antiproton. This is proton-nucleus collisions. Proton-proton collisions, sorry. And we can find single functions that simultaneously describe these as well. So the idea is to get predictions from fits to data such as these, again, where no entanglement is expected. So this is another quark-antiquark annihilation to electromagnetic final state. And then here at my Phoenix experiment at RIP, we've actually already published this, motivated by heavy ion physics, actually. So we're looking now at PP to a 2-hadron final state, a neutral pion and a charged hadron on the other side. And they're nearly back to back. We look at the out-of-plane momentum component between the 2, which is sensitive to the intrinsic transverse momentum in the quark-gluon scattering process and in the process of hadronization. And so these are different transverse momenta. These are like different hard scales. So this is versus the quantity on the x-axis. This is a cross section or yield. The quantity on the x-axis is sensitive to intrinsic transverse motion of the parton. And these going up are different hard scales. So different invariant masses here, different transverse momenta here. And I don't have plots, curves to show you yet. We're still working on this. This is work in progress. Of course, my dream is that it'll be a 6 sigma right away. Usually you spend some years in the muck with your 1.5 sigma results before you hone down your uncertainties, either on the theory or the experiment to really get a conclusion. But I can keep dreaming until I get those curves. So to summarize, I think we're in the early years of a rewarding new era of quantitative research in QCD. We've been gradually shifting to think about QCD systems in new ways, focusing on ideas and concepts that have long been familiar to the world of condensed matter physics, such as all sorts of correlations within QCD systems, quantum mechanical phase interference effects, quantum entangled systems, and I think it'll be exciting to continue testing and exploring these ideas and phenomena in the upcoming years. So thank you.
Any questions?
I didn't leave much time for questions.
Comments? So can you tell us more about the studies of the C boson? What is the is this data from the tevatron? Is that for the experiment that you?
What I showed there was from the tevatron. Yeah, we have a couple points from the LHC. They don't have. I guess they haven't been interested. They don't tend to have very good PT resolution at 1 to 2 to 3 GeV. So it's.
That's the trouble.
Yeah. Well, they're not
Actually,
focused there.
is this phi something variable at
D0 uses.
D0
Yeah.
used? I think it's experimentally very robust and might be sensitive to this.
Yes, it
I don't
is,
really
yeah.
understand what the difference is between the two models would be.
What do you mean, the two models?
Are you showing the black compared to the red?
Oh, sorry, no, that was the plot that I should update. This was what we were talking to the Rochester group on CDF that was doing this analysis at the time that we got started before they'd published it. So this was an internal preliminary note plot that showed there, yeah.
But the prediction is just a different PT distribution
The-
with and without entanglement.
So the prediction. So these are fixed to data where we don't expect entanglement. So I'm fitting the black points here. So these are these points. I just replotted myself with my fits that are. I'm using functions that can simultaneously describe 8 different experiments, just like CTEC or whatever does the traditional collinear PDF fitting with global data. And so this is other old fixed target Drell-Yan data that's going into our fit also. And then this is an observable where you would expect color entanglement, so we're not fitting this. We're going to take the fits that we do from all the world data that we can get our hands on where no color entanglement has been predicted to try to get the best constraints on these transverse momentum dependent parton distribution functions. And then just pretend there's no entanglement expected here, make a prediction, a naive prediction, and then see if the slope and or magnitude is different, is the idea. And the hope is that it's a big enough difference that we can make some kind of statement, and we'll see. Get a bit confused.
So you're hoping then that these type of effects
Yeah.
can be pulled out without the experiments as they're currently designed?
That's the hope. That's the hope, but if nothing else, we'll learn something about how we need to design better experiments, which may well be the case. Yeah, the theorists, I asked the theorists if they have any idea what kind of you expect, what kind of magnitude effects, and they couldn't give me any numbers, so I don't know. We could well be chasing after something that we can't measure for another 10 years with sensitivity, so there's some, people can't make the PP 40% asymmetries agree with the semi-inclusive DIS data, which is already sort of a hint that there might be big effects there, but the reason I am working with the unpolarized data is because we have 40 years of unpolarized data, so the transverse momentum distributions of all the old Drell-Yan experiments and a lot of tevatron data that has pretty good PT resolution down to these low transverse momenta, and a few points from the LHC, even if it's 1 or 2, but they're at such a different scale that's kind of helpful also in constraining. So we're working with the unpolarized data now. People should be doing these fits anyway, so we'll improve the fits, so that'll be published. We have one paper published so far on the Q-squared evolution, which is more complicated because there's non-perturbative input, unlike the collinear case where you just have the D-glass equation. So that means anything to some people. Who knows, but
Are there any other comments or questions? No, thanks a lot.
Okay.